Okay, class, welcome back. Today we're going to be talking about triangles some more, and specifically we're going to be talking about some special angles. And so we're looking at function values for some special angles. Now, the purpose of this lecture is to help sort of identify, highlight, reiterate some things that you might already know, but maybe to put a new spin on it and also to emphasize the importance of it. So the angles we're going to be looking at today is going to be pi over 4 radians, which is 45 degrees, pi over 6 radians, which is 30 degrees, and pi over 3 radians, which is 60 degrees. Now, hopefully you guys have gotten these memorized, or at least they're familiar enough you can figure them out. And so we're going to look at these special angles, and we're going to be trying to figure out what the sine of 45, the cosine of 45, and the tangent of 45 is. But instead of doing it from the unit circle perspective, we're going to do it from triangles. And it's definitely going to cross over, and we're going to end up with the same answer as the unit circle. But once again, it's that connection between angles, the unit circle, triangles, the sines, the cosines, all of those connections that I really, really want you guys to understand and have a deeper understanding of. And so if we're looking at a 45 degrees, right, and we're going to calculate this with triangles, right triangles. So I've got my right triangle. I've got some angle here, which is 45 degrees. And then I'm going to have another angle here, because the interior angles are all going to be 180, and the other angle is going to be 45 degrees as well. So this is an isosceles right triangle. It's a very special triangle. It appears all the time. It's very, very common, and we're going to use it to investigate what the sine, cosine, and tangent of 45 degrees are. And so if we look at this, I'm going to start just by labeling this. Of course, the length, the base, and the height of this triangle can be anything that I want it to be, but in this case I'm going to keep it simple, so I'm just going to say 1. So the base is 1. If the base is 1, then the height has to be 1 because it's a right isosceles right triangle. And then if I try to figure out what the hypotenuse is, I can just say a squared plus b squared is going to be equal to c squared, a and b being 1, so I say 1 squared plus 1 squared is equal to c squared. Or I can just say 2 is equal to c squared, or then just c is going to be equal to the square root of 2. So here I've got the square root of 2. That's going to be my hypotenuse. Fantastic. And now with this information, I can figure out what the trigonometric function values for 45 degrees are. And this goes exactly into the stuff we were talking about yesterday. So here's the first example. Is I want you to find, or we're going to look for the 6 trig identities, or at least the 3 main ones for 45 degrees. So we're looking for find sine of theta, cosine of theta, tangent of theta for theta is equal to 45 degrees. Or I'm going to put pi over 4 radians. Okay, so if I'm looking at the sine of theta, so here I'm going to take a look at my triangle just from this angle right here, theta. And so then I know that the sine, if you remember the ABC thing we did yesterday, if you want to remember SOHCAHTOA, so you can say the opposite over the hypotenuse. So the sine of theta is going to be equal to 1, which is the opposite side, and the hypotenuse is going to be root 2. Now, of course, I can't have a radical on the bottom, so in order to get rid of that, I multiply the top and the bottom by root 2 over 2. The top 1 times root 2 is just going to be root 2. And the bottom root 2 times root 2 is just going to be equal to 2. So here I've got root 2 over 2. So this should be looking pretty familiar from the unit circle stuff that we did. Next is the cosine of theta. Now, of course, this is CAH, or Ka, which means I'm going to take the adjacent side and divide it by the hypotenuse. Now the adjacent side is the same as the opposite side because it's an isosceles triangle. So I've got 1 over root 2 is going to be cosine. Of course, I've got another square root of 2 on the bottom, so I need to do the same operation to get rid of the radical on the bottom. And so I end up with the square root of 2 over 2. This is looking pretty familiar too. So the cosine and the sine, square root of 2 over 2, comma square root of 2 over 2. This is one of the points on the unit circle. Now the tangent of theta, this is our TOA. So if I go opposite over adjacent, or 1 divided by 1, then I can just say 1 divided by 1, which is just going to be equal to 1. Now check this out. If I also did sine divided by cosine, which is going to be tangent, tangent sine divided by cosine, or y divided by x, I'm going to equal with 1 all the same. So no matter how I'm calculating these angles, if I'm using triangles, if I'm using the unit circle, I'm coming up with the exact same answers. Pretty cool. Now, I do want to point out one thing. If we're using the unit circle, we get these same answers. If we're using this triangle, now the triangle we started with yesterday was based off of the unit circle, so it had a base of 1/2 and a height of root 3 over 2. However, this triangle right here is not on the unit circle. Can anybody tell me why? Think about it. Well, it's not on the unit circle because this radius right here is not 1. Remember, that was the characteristic. So if I was to draw a circle sort of around this, and we were thinking about x and y, and this is going to be our radius, it's the square root of 2. It's not 1. So the square root of 2 is about 1.414. It's not going to be on the unit circle. However, using this triangle, using triangles, we can find the exact same values for what the sine, the cosine, and the tangent of pi over 4 or 45 degrees are. Pretty cool. Now, we're going to do the same thing with excuse me, pi over 6 or 30 degrees. But the first thing we need to do is, of course, figure out what our triangle looks like. So I'm going to draw my triangle here. A little bit of an exaggeration. But say this is going to be pi over 6 or 30 degrees. So this is 90, this is 30. You guys can do some super quick math and determine that this angle right here is going to be 60 degrees. Now this is a 30, 60, 90 triangle. This is very, very special. And one of the properties that a 30, 60, 90 triangle has is that whatever this side is, the short side, and in this case I'm just going to label it as 1, this long side is twice its length. Right? So if this is 1, this is going to be 2. If this is 5, this is going to be 10. Okay? So this is similar to a problem we had yesterday. The first thing I need to do is I know the adjacent or the opposite side, and I know the hypotenuse. I know A and C. I need to figure out what B is. So I'm going back to a squared plus b squared is equal to c squared. And so I can say 1 squared plus b squared is going to be equal to 2 squared. Or 1 plus b squared is going to be equal to 4. Subtract 1 from both sides, and I basically get b squared is going to be equal to 3, or b is going to be equal to the square root of 3. 1, 2, square root of 3. This is a very, very common triangle. It's used all the time in a lot of different settings. But now that I've got the triangle figured out, I can start finding out what the sine, the cosine, and the tangent of 30 degrees is. Okay, so I'm going to be looking at, once again here, theta. So I can say, okay, the sine of theta is SOHCAHTOA. So I go opposite over the hypotenuse. So I can say, okay, this is going to be 1 over 2. Easy, nothing to it. Now the cosine of theta is going to be equal to, I'll move down here. Cosine of theta is going to be equal to, we're talking about the adjacent over the hypotenuse. So right here, 3 square root of 3 over 2. Square root of 3 over 2. Fantastic, just like that. And the tangent, hopefully you guys are ahead of me, the tangent of theta is going to be equal to the opposite over the adjacent. So we've got the opposite right here, which is going to be 1, over the adjacent right here, which is going to be the square root of 3. Now, of course, I can't have this. I've got a radical on the bottom, so I need to multiply by square root of 3 over square root of 3. Now, this is going to be equal to, on the top, I get 1 times the square root of 3. And on the bottom, I get root 3 times root 3, which is going to be 3. So I get root 3 divided by 3. Sine, cosine, tangent, just like that. Now, I can do the exact same thing, finish out this lecture, if instead of doing 45 degrees or 30 degrees, I now did 60 degrees. So here I'm going to have a tall triangle, and this is going to be pretty much the same triangle that we just did. It's going to be exactly the same triangle. I'm just redrawing it and rotating it, basically. So this is 1, this is 2, so short side is 1. The hypotenuse is going to be 2, and you remember the other side over here is going to be root 3. In this case, it's going to be the height before it was our base. So now, once again, I'm looking for the sine, the cosine, and the tangent of these values. Okay, so here I've got the sine of theta. In this case, my theta is going to be 60 degrees. So sine of theta SOHCAHTOA. So I'm going opposite, which is going to be root 3 over 2. Hypotenuse being 2. Cosine of theta is going to be equal to, so in this case I'm looking at the adjacent. The adjacent is 1. So CAH, adjacent over the hypotenuse, over 2. And now finally, to round it out, I've got the tangent of theta, and this is going to be the opposite over the adjacent, or TOA, TOA. So I've got the square root of 3 divided by 1. Square root of 3 being the opposite, and 1 being the adjacent side to this angle right here. Square root of 3 over 1. Now make sure you reduce this fully just to square root of 3. Fantastic. Just like that. Okay, now the last thing I want to point out is you can fill out a table really simply that sort of summarizes all of this stuff. Okay, so right here across the top I've got theta, and then so here I've got 30, 45, and 60. This is just basically summarizing all the stuff that we just figured out. And down the side I've got sine of theta, cosine of theta, tangent of theta. Now, this is going to look really similar to when we were filling out our unit circles, but across the top right here, this first one, it just goes 1, 2, 3. The second one goes 3, 2, 1. So we go 1, 2, 3, 3, 2, 1, just like this. Now, of course, they're all over 2. And if you've got more than one person, then everybody needs a party hat, right? Because you get a party, just like this. Done. So that's it. So the sine of 30 degrees is 1/2. Sine of 45 is root 2 over 2. Now tangent's a little bit trickier. You might need to do some math here. So basically you just do sine over cosine. So 1 over 2 divided by root 3 over 2. You end up with root 3 over 3. And we just did that calculation. Here we've got root 2 over 2 over root 2 over 2. So the same thing divided by itself is just going to be 1. And then here we've got root 3 over 2 divided by 1/2. This is just going to be equal to root 3. Fantastic. All right, guys. Look forward to seeing you guys in class tomorrow. We'll work on some problems involving this stuff.